something to say about competition?
Yeah, this weekend we have 2 teams of students going to the ACM Regional Programming Contest. One team of 400 level students, one team of 300 level students. So Dr. Stauffer will post on our website a little bit of information about it and the link to a website where you can watch their progress. Their names of the teams are, this is going then, SSU1 and SSU2. Lesson team.
Less is more.
Where is the competition? Stand. I'll stand.
Okay, now that my family colleagues are here, we'll start. So it's a pleasure and an honor to introduce Jim Horning, who is a legend in the computer science profession. Today, he will tell us, I hope, 2 things. One is infrastructure and why we should bother. And the second thing, I think, is why or what is Sparta. So, let's introduce.
First, let me give you best wishes for the programming contest, and hope you will do something to bring the World Championships back to the United States. Been going to Russia and Poland and China in recent years. Second, I'm not going to tell you what Sparta is, other than it's a government contracting company. Third, interrupts are enabled. I intend this talk to be provocative rather than authoritative. Therefore, I expect that you will have questions, you want to challenge me on points that you'd like to dig deeper someplace or whatever. Feel free. So, kind of a jumble of topics I'm planning to cover, starting with definitions of what is infrastructure and what is maintenance. It's old history, it's new history. Talk about maintaining civil infrastructures, and then a little bit about maintaining software, which has quite a bit in common and a few differences. I'll mention a couple things that I don't consider to be software maintenance, although they're often called that. Talk a bit about SCADA systems, and then leave you with a puzzle and some further reading if you're interested. So, how do I decide what infrastructure is? Well, I do probably what you do. I type infrastructure into Google. Look at the definitions that pop up and pick the ones I like. But there are some recurring themes from these various definitions that I found. One is it's something that underlies a society or a system. Another is that it's essential, it's not optional. And another is that it is very dependent on the state of the civilization or organization to which it pertains. And so when we get down to computing infrastructure, that includes the hardware, the networks, includes the operating system, the database management system, communications protocols, a whole bunch of things that the person providing a service doesn't want to think of. It should just be there. Like when we walk into this room, flip a switch and the lights come on. We don't worry about turning on the generator in Washington State or something. It is necessary to provide us the electrical power. What is maintenance? Maintenance is the work of keeping something that's already working properly. It's designed to make it perform its original function. And it's typically something that is done recurrently. For an airplane, it's every few thousand landings or a few hundred landings, depending on the subsystem. For other systems, it may be measured in hours or years. And so for software maintenance, I say it's going to be the recurring updating of programs in order to continue to operate as was intended when the program was developed, but in a changing environment. So, it's an ancient history. It suggested that much of the power and longevity of the Roman Empire was due to its heavy investment in infrastructure. Three of the key infrastructures were the roads, their technologies for acquiring and distributing food, and perhaps the most spectacular were their aqueducts. And I listed from a web page a timeline of Roman aqueducts. They were built over a period of about 550 years. Originally one aqueduct supporting a city of a few tens of thousands of people. At its peak, they had 11 different aqueducts supplying a city of 1 million people. As the invading German tribes kept marauding and destroying pieces of the aqueducts, they eventually ended up with just one aqueduct, the very first one they'd ever built, which was underground and much harder for the Germans to get at. And it supported a city of about 30,000 people for another nearly 1,000 years. This is an example of a lack of maintenance. So, some more recent history. There has been a lot said, and I've been hearing it and reading it for at least 25 years now, that America is underinvesting in its infrastructure, that it is not keeping its roads, its bridges, its dams, its electrical power system, all of its infrastructures in as good a shape as would be necessary to keep it functioning as originally intended. And over the last 25, 50 years, there have been a number of very costly failures of parts of this infrastructure that could have been prevented by timely maintenance. I'll talk about a couple. As I say, American engineers have been very loudly and formally complaining about this for a quarter of a century, but people have not been doing as much about it as they consider appropriate. So I picked this particular picture of New Orleans because it's like a puzzle picture. How many things are wrong with this picture? How many different infrastructure systems can you see that have failed or deduced from the picture that have failed? One of the ones that I didn't notice until about the third time I looked at it was up there on the edge of the water line. There's a great plume of smoke. You might not think that a flood would interfere with the firefighting infrastructure, but in fact it does in many severe ways. So, there was a hurricane you've all heard of called Katrina that hit New Orleans on August 29, 2005, a little over 3 years ago. And this caused a cascading series of problems. There was some wind damage. The wind caused tidal surges, so-called tidal surges, that raised the water level around the levees. The levees, many of them, were not only overtopped, but collapsed at their foundations. And great parts of the city were flooded, including the parts that contained much of the electrical infrastructure, contained the pumping infrastructure to get water out of New Orleans, much of which is below sea level. Telephone system largely failed. Water and sewer systems largely failed. Of course, hospitals, schools, police services, transportation, libraries, banks, you name it. The city shut down. And the absence of each one of these infrastructures made it harder to repair the others. You can't repair the pumps without electricity. You can't get the electrical substation working until you can pump the water out. And all kinds of interdependencies. Now, the interesting thing, perhaps, about the New Orleans collapse was not only was it predictable, it was predicted in quite some detail by numerous civil engineers. Everything from how the levees would fail to why they were not as tall as they should have been, had not been maintained properly, to what the consequences of large breaches in levees would be. But it would have cost many millions of dollars to have listened to those engineers and done something about it. Perhaps tens of millions of dollars. So instead, we have a situation with more than 1,500 people dead, over 100 gigabucks of federal aid alone. Imagine what could have been done to shore up the levees with 100 gigabucks. To have shored up all of the different infrastructures with 100 gigabucks. 100,000 people were trapped in the city because the infrastructure for getting them out failed. Public transport and the highways. 250,000 people were turned into refugees. Many of them are still refugees 3 years later. And a figure I picked up from the New York Times, it'll probably take as long for New Orleans to recover as it did for San Francisco to recover after the 1906 earthquake. It's about 20 years to be back as a fully functioning city in the same sense that it was the day before Hurricane Katrina. Okay, here's an even more recent example. Minneapolis Highway Bridge. I'm sure you've read about this and seen it on the news. At rush hour one day, it collapsed. I mean, it really collapsed, not the way the Oakland Bay Bridge just dropped a section. This really destroyed itself. As with all disasters, there were multiple causes. The design itself was faulty. It was, in post hoc analysis, it was realized that the designers had not done a proper job in designing the bridge. In particular, they had specified 1/2-inch thick gusset plates instead of 1-inch thick gusset plates. Now, gusset plate is probably not your working vocabulary, but when beams come together on a steel bridge, there's a steel plate that is used to join the beams. That's the gusset plate. The other problem was that the style of design used for the bridge was fracture critical. What this means is that any single gusset plate failing would put an excessive load on another gusset plate, triggering its failure, which would put an excessive load on yet another, triggering its failure. Modern bridge design calls for having enough redundancies that if any single gusset plate fails, there are others that can take the load. This was not the case for that particular bridge. 2 years prior to the collapse, during a routine inspection, they took photographs, which, again, analyzing after the collapse, clearly showed that the gusset plates had already started to buckle. For 17 straight years, the bridge had been inspected by highway inspectors and rated as poor. But it never rose on the priority list to where maintenance got funded. And then finally, there were tons and tons of sand, gravel, and construction equipment on the bridge right above the critical points, waiting to be used to resurface the highway. The result was 13 people killed, 145 injured, a $38 million compensation package for the people who've been on the bridge when it collapsed, and a 400 megabuck replacement bridge being built on an expedited schedule at much higher cost than had it been replaced in its intended time span. Fascinating details on this. I could talk all day, but it's not my primary subject. But the Minnesota Department of Highways has a website with dozens of pictures, with minute-by-minute chronology, with explanations of exactly what failed and when and why, and what people did about it. So to return to my main argument, civilization and infrastructure are intimately intertwined. If you have a rising civilization, it will build new infrastructures which will enable it to rise even faster, which will enable it to build more and better infrastructures, and so on, in what's called a virtuous cycle of positive feedback. However, there's another side to positive feedback, and that is, if you start going down, every increment of infrastructure you lose detracts from your capability to support, maintain, build infrastructure. And I'm not saying there's a causal relationship here, but certainly temporally, it happens at the same time that the infrastructure decays and the civilization collapses. Maybe leaving some remnants behind, like those aqueducts, like some of the Roman roads that you can still follow in Britain and parts of Europe. But the civilization was gone. Now, in the modern world, all around the globe, not just in this country, we're increasingly depending on more and more infrastructures that are getting more and more complex and more intertwined. This is not just information systems, which is what we tend to think about, the internet and all its interconnectivity and interactions. But the electrical grid, the natural gas system, the petroleum supply, the highways, telecommunications, they are all heavily codependent. And almost all of them rely in a fundamental way now on information technology. And people like this. People appreciate improved service, more support, more things that they don't have to think about, more things that they can use without understanding. But there can be a problem if no one understands the whole system. And if you'd like to read a very prophetic short story, I would suggest for you one called The Machine Stops by E.M. Forster. It's about 100 years old, the story is. But it's a remarkable projection from that day into the future of what highly integrated infrastructure would be like and what would happen when it started to decay. As we've seen in both of our recent examples, and is true in many, many more examples, when one infrastructure fails, that tends to cascade and cause other infrastructures to fail, which cause other infrastructures to fail, etc. Therefore, repairing the damage, getting the system back to where you want it to be after a failure, can be much harder than it would be to fix any single system, or even the sum of the difficulty of fixing the single systems. Going back again to New Orleans, the electricity electrical substations and the pumps, for example. It was much more expensive to get the pumps running without electrical power and pump out the electrical subsystems so they could then start to power the pumps than it would have been if only one of the two had failed. So some of you are probably engineers or pre-engineers, and certainly something that is taught to engineers in general, but civil engineers in particular, is that physical infrastructures decay. There's erosion, there's corrosion, there's stress fatigue, there are just lots of different things that cause physical devices or systems to wear out. And therefore, physical infrastructure must be inspected and repaired, i.e. maintained. And such maintenance is usually the cheapest form of insurance that you can get against the failure of that system. If you ask an insurance company to insure you against your car running without oil changes, the premium would be higher than the cost of the oil changes. There are a few cases where this is not true, such as spacecraft, where you simply cannot get access to new maintenance once you've launched it out towards Pluto. But those exceptions are rare in the engineer's experience. But it is still sometimes, perhaps even often, given short shrift, not by the engineers, but by their managers. And the reason is that maintenance costs now. The failure is sometime in the indefinite future, and you don't know how much it will cost. And if you can't quantify it, then why not ignore it? So now, turning to software maintenance. We know the computer software doesn't erode or corrode. Ms. George, you pointed out to me that software is rust, sitting there in the oxide of those spinning disks. But in the normal sense, bits don't rot. But nonetheless, software systems do decay. And that is because the environment in which they are operating invariably changes. The only constant that you can be sure of is that things will be different tomorrow. It's still more different in 5 years, it's still more different in 10. And because things keep changing, in order for the software to continue to do what you intended it to do in the first place, you're going to have to go in and maintain it. You're going to have to inspect it. You're going to have to check whether its assumptions are still met. You're going to have to check whether the patterns of usage are indeed the patterns for which it was designed. And yet when people are planning and budgeting for critical systems, they very rarely put in software maintenance as a continuing expense of the system. The assumption is, oh, we'll get it right. Now, 60 years of not getting it right have not yet got the lesson sunk in. And something that makes it even worse is that systems are not merely in changing environments, but the systems themselves change. The function that we want tomorrow, next week, next year is a little bit different from what we wanted today. So, we change it without necessarily rechecking all of the assumptions that were implicit in the original design, meaning that it is no longer quite as suitable for the original purpose as it was before, or maybe drastically less suitable. So a couple of examples, and I realize Y2K seems like a long time ago to some of you. But what seems like a long time ago to me was the 1960s, when memory cost $1 a byte, and RAM from IBM. Saving 2 bytes in every date was actually a significant economy that was worth doing. And so most systems written in the 60s and 70s, and many even in the 80s and early 90s, used 2 digits to represent the year and a date. And somewhere along about the middle of the 90s, some people started screaming, hey, you guys realize that year 0 is coming up real quick now. And you've got a lot of systems that were written by people who have retired and are no longer available to tell you where they made these assumptions, who didn't document where they made these assumptions. You have to go in and find and fix all of those places. There was a brief employment boom for retired COBOL programmers to come back out of retirement because they could at least read the code even if it hadn't been documented. But you can't really blame the guys in the 1960s who made reasonable assumptions, had no idea that their program would still be running in 40 years. Nobody thought software would last that long. People thought it was hardware that was persistent and software that's transient. Of course, it turns out, in fact, hardware is easy to change, replace, and it's software that we have this huge legacy that we have to deal with. And that is why we must maintain it. It's going to be around for a while. Just this week I read about the launch of Global Positioning Satellite 32 and the fact that a lot of GPS receivers, at least from one manufacturer, will stop working whenever that satellite is in radio range. And I don't suppose you can think of anything about the number 32 that would cause that to be the case. But it was necessary in order to maintain the original intended function of the software in those GPS devices, go in and do some maintenance. So, having told you a bunch of things that are necessary for maintenance, let me point out that there are 2 things that are often called maintenance that really aren't. One is adding some new functionality, which I would prefer to call software extension or something like that, or just add new functionality. When you add a new wing code building, you don't normally call it maintenance. And the other thing, and this is the one that really gets to me, is the patching of bugs. Patching bugs in programs that never function as they were originally intended to function is just belated quality assurance. Now, both of these are important activities, and you ought to be doing them. But you also ought to be doing software maintenance. Make sure that the software continues to do what it was originally intended to do, and hopefully it still does. So, with all these arguments in favor of doing software maintenance, why is so little of it done and so little of it taught? Well, it's hard to design a system that will be easy to maintain. When you design the Golden Gate Bridge, you realize you have to leave inspection ports in the towers that people can climb up and inspect all the joints inside as well as the exterior ones. But civil engineers have centuries of experience in how to make things inspectable. Most computer programs are not very easy to climb around and discover where the stress is starting, where something is about to break or might break. Getting this done is going to cost you more, and it's going to require some people who have some skill in it, of which there are unfortunately not very many. So the easiest path is just to not worry about maintenance at all. Hope it won't bother you. However, I believe that the economy as a whole, the companies, individual people writing and selling software would all benefit from planning from the start for maintenance and then religiously doing it. Now let me shift gears a little bit to SCADA. You all know what SCADA is? You should now because it's the title of the slide. But supervisory control and data acquisition systems run virtually this country's and most countries' entire infrastructures, or at least great chunks of it. And SCADA systems are built out of software. Some hardware too, but software is a critical element. SCADA systems are one place where you definitely know the lifetime is going to be long and change is going to be inevitable. So this is where software maintenance and civil infrastructure maintenance meet. Or some people say it's where they collide. And to make things even scarier, most SCADA systems are either already connected to the internet or will be within a very small number of years. Why? This means that the home office can call up the plant in Idaho and see exactly how things are doing. The marketing department can use that information. The accounting department can use it. Let's just put it on the web. Which leads us to the topic of security or insecurity, about which I can give you another whole lecture or series of lectures. Just yesterday, Amazon delivered to me a copy of Ross Anderson's new book, or new edition of his book on security engineering. It's literally 4 inches thick. I think the biggest book I've gotten from Amazon. I need to read. Because the internet is inherently insecure, it provides vandals and saboteurs easy access to the entire internet and relatively easy access to anything connected to the internet. There have been some small victories on the way. I don't know whether you read, but there was one web hosting provider in the Bay Area that was shut down on, I believe it was Monday. And worldwide, global spam traffic dropped by 65%. One web hosting provider, that is. It turned out what had been discovered was this was where the bot masters were putting the instructions for all their botnets to pick up information about what spam to send next, close that off, shut down 2/3 of the world's spam. Won't last, but enjoy a spam-free week. Yes?
Out of curiosity, if they are able to recover their infrastructure to pop the spam levels back up within such a short amount of time, is there any way that we can use their techniques to make our infrastructure more resilient?
That's a very interesting topic of research. Some of the techniques would be illegal. Effective but illegal. There have been, in fact, several cases of security researchers who have infiltrated the command and control structure of botnets. But to go in and do anything with or to those bots would be illegal. Now that doesn't bother the spammers, but it does bother reputable university researchers or reputable industrial.
Even if you didn't get into their network, the botnet networks,
Yeah,
shutting them down using their own protocols would be illegal.
yeah. For the same reason that they're getting into your computer at home and telling it to send spam is illegal. You are not allowed to send instructions to a computer that is not supposed to be receiving.
That's kind of fun.
Felony, I believe. Certainly there are fairly heavy fines associated with it if you can catch the guys. Of course, the people you have to catch are probably in some place like Belarus or Bulgaria or someplace with which we don't have really good criminal justice ties. So yeah, it's fascinating to try to figure out how much you can do and say within the law and yet still reduce the effectiveness of the botnets. Good thesis stuff. So I just wanted to wrap up by leaving a puzzle for you. If you buy my argument about the importance of software maintenance, why is it that future software engineers don't get very much training in software maintenance? Now, I'd be happy to learn, that that's not the case here, and that you've all been taking courses in software maintenance and understand fully how to design for maintainability, how to prepare for software that's going to age, how to maintain legacy software and keep it performing its original function. And perhaps the hardest one is knowing when and how to terminate a system that is past the point of maintainability. There comes a point in the life of any system where fixing one problem generates 1 plus epsilon problems on average. And at that point, you really have to stop maintenance. If maintenance has stopped, then you really shouldn't be relying on that system anymore. And if you shouldn't be relying on that system anymore, why are you still running? And what software engineers need to understand is how to explain this clearly to their managers and the executives who control budgets. So, a couple of lists of places you can go to read more about some of the things. What I said about Roman aqueducts mainly came from Michael J. Asenti's article, which, as far as I know, is not available in a hard copy, only on the web. And unfortunately, it has a very long URL. Screw it, guys. The report from 25 years ago that I referred to was Duke University Press. The National Academies Press report 5 years later. That's 20 years ago. Library of Congress back in 1991 collected a bibliography on the maintenance of civil infrastructures. It is still highly pertinent. And there are continuing books, articles. And then on the software side, there actually are at least 2 fairly reputable, long-running conferences on software maintenance. I believe they use a more expensive definition of maintenance than I do, but a fair amount of what is talked about there, in fact, bears on questions we've been discussing today. Peter Nyman and I wrote a column in Communications to the ACM, which I trust you've all read. You all read the ACM, don't you? Again, a book from 1995, Will Trace. A very nice book that bears on this. There is a regular newsfeed called Risks Digest, edited by Peter Neumann, that is just full of the sorts of examples that I only had time to give you a couple of tastes of today. It's well worth subscribing to. There's some very amusing things that happen with computers, as well as some very tragic things. Like every year or so, there is a legitimate news story about someone who has followed their car's GPS system to the ferry dock and right on out to where the ferry would be if the ferry were there, without bothering to confirm with their eyes. I think that's a reasonable thing to have done. My car, at least, every time I turn on the GPS, it makes me explicitly acknowledge that this is only advice and not to be relied on. And then there's a somewhat condensed version of the Risk Digest that appears with just one-line descriptions of various things. So if you'd like to find out what's been happening recently with banks or what's been happening recently with sewer systems, or with GPS, you can go there and find out where to track back for more information. So, you've been very patient. Are there any more questions?